and then these nucleus will grow into grains. Can you recall or not? Nucleation. And there are two nucleation mechanisms. What are the two nucleation mechanisms? Homogeneous nucleation, and the other one is what? Heterogeneous nucleation. You can control the grain size by controlling the what? Nucleation process. Let's talk about homogeneous nucleation first. Homogeneous nucleation. Okay. Can you remember in homogeneous nucleation? In homogeneous nucleation, you need to have what? What is the driving force? Undercooling. That means you must cool to below the what? Melting point. Alright? Melting point and freezing point are interchangeable. They are the same, not. When you heat up, it goes through the process. Then when you cool down, it goes through the same as well, Alright? So you must have what? Undercooling. Undercooling is the what? Driving force. Remember that? Alright? The more undercooling you have, okay, the easier you will get the nucleation. Okay. Now, in homogeneous nucleation, alright, it is very important you must have the minimum size. The nucleus must have a minimum size. The minimum size is measured by what? The radius. This minimum radius is called what radius? Critical radius. Anything less than a critical radius, okay, you will dissolve back into the liquid. Okay. Now, can you also recall, okay, why that more undercooling will give you fine grain size? If I ask you to explain this to me, can you or not? More undercooling will give fine grain size. How come? Because why? The critical radius is what? Inversely proportional to the undercooling. The more undercooling, the smaller the critical radius. And I have given you a very simple illustration, correct or not? If your critical radius is small, then it is easier for you to get what? Radius which will be able to be, which are stable and continue growing. If your critical radius is very large, then only very few what? Nucleus will have that size, So you don't have that many, what you call that, stable nuclei. Nucleus is what? Singular. Nuclei is what? Plural. Nucleus, nuclei. Okay? Alright. So you know about undercooling, Alright, you know about homogeneous nucleation, So just give it more undercooling. Alright, How do I get more undercooling? How? It depends on what? How much undercooling I have, depend on what? The what?
Surface.
No, not surface. I want to have a lot of undercooling. What do? I cool very fast. Remember or not? That's why your surface will give you what? Chill grain. Why your surface give you chill grain? Chill grain are small grains. Because why on the surface the cooling rate is very fast due to what? Heat conduction. Alright, so fast. More undercooling, small critical radius. Alright, then I will end up with what? Fine grain size. Okay? Alright, that is homogeneous nucleation. And remember, I told you the formula? Alright, to work out what is the critical radius, you look at your what examples in your book. Alright, work it out. Remember, your temperature must be converted to what? Kelvin. That means degree centigrade must add what? 273. Okay, but the undercooling is what? The temperature difference. The one you don't add 273. Alright, because the upper temperature you add 273 minus the lower temperature add 273. Okay, the two times 273 minus 273. No need. Are you clear or not? Okay. Alright. Okay. Now, heterogeneous nucleation. Do I need undercooling? No. What do I need? I need what? Nucleating what? Agent. These are what? Foreign particles. But these foreign particles, I told you, must be what? Suitable foreign particles. That means they must have what? Compatible what? Size. Or crystal structure. Compatible crystal structure. Alright? Otherwise, I have a pot of what? Molten aluminium, I just go and sweep some sand and then I dump it inside, it won't work, not. Alright? You must add a correct size. Are you clear or not? Okay? So, these foreign particles will act as the what? Stable nuclei. Alright? That means the more I add, the final will be the what? Grain size. Correct or not? The final will be the grain size. So, for heterogeneous nucleations, if I want to have what? Fine grain size, what do? I add more of this nucleating agent. What are two other names you give to this nucleating agent? You can also call them what? Grain refiners or what? Inoculants. Okay, you can call them grain refiners or inoculants. Okay, so do you have any issues? Do you have any issues or not with what? Nucleating mechanism? Are you all okay or not? Comfortable? All comfortable? Okay, two nucleating mechanisms. Okay, now grain size, strengthening. Okay, the finer the grain size, the stronger will be the materials. I think this one is explained by this. You tell me you have not done it before, so I don't know. When you talk about what do you call that? Plastic deformation. Right? Plastic deformation. There is this, atoms have to what? Move. Atoms have to move, slide. Okay? This, you said, it has been explained to you in terms of what? Shearing. Alright? So these atoms, when it moves during shearing, okay, the movement is called dislocation. Have you come across that before? You got what? Edge dislocation, you got screw dislocation, all these, These dislocations, okay, when it moves, the what do you call it? The materials will then deform, But when this dislocation comes to grain boundary, you need more energy to push it across the grain boundary. That's why the grain boundary will act as an obstacle. So, if I got more grain boundaries, means what? I need more force to push all these dislocations across, which is end up with what? Your materials become stronger. I need more force, to force them through. Alright? That is why fine grain size, fine grain size? Fine grain size, okay, will make your material stronger. Because you add up the total amount of what grain boundaries is more than one big grain, Okay, just like your lungs, your lung is super efficient in sort of, for oxygen diffusion. Because why? It consists of what? Very, very tiny air sacs, Alright, so you actually add up the total surface area is very, very big, the lung. Okay? Alright, now, I can actually have various mechanisms to actually, have this second phase. I can add directly, okay, as solid particles, or I can also add what? As alloying elements. When I add as alloying elements, the alloying elements can react. Okay, just like in the case I have given you titanium and boron, titanium, aluminium, all these, when they react, they form what? Particles. These particles will then act as a what? Nucleating agent. Are you clear now? So you can add it as what? Alloying element, or you can add it as what? Solid particles. Okay? Alright. Okay. What else did we talk about? Okay. Now I'm just running through to make sure you understand, Alright, Okay. We have got growth, we talk about nucleating mechanisms, we have got homogeneous nucleation, we got what? Heterogeneous nucleation. When we talk about growth. Alright? There are two types of growth, dendritic, and the other one is what? Planar. Dendritic means what? Refers to what type of nucleation? Dendritic? Homogeneous. Because dendritic must have what? Undercooling. Planar got no undercooling, planar. So the surface, alright, of the solid will act as what? The nucleating surface. So nucleation will take place on the surface. So the surface will be what? Growing as a plane. Right? And on the surface there are many grains. Each grain will keep on growing. So you end up getting what? Columnar grain. Are you clear now? Longish grain. Okay? I think we have talked about the ingot structure where you talk about columnar grain, isn't it? You remember or not? Okay? Alright, so we have got what? Dendritic growth, and the other one is what? Planar growth. Okay? Okay, now, this one, take note. There is a, what do you call that? Formula that tells you about solidification time. Remember or not? Okay? That is, the formula is under what rule? Reynolds rule. Reynolds rule. Okay? You know, remember the what you call it, the formula? Maybe the one, you just remember this, okay? The solidification time is proportional to what? Is proportional to what? The volume over the what? Surface area of the casting. You know the casting? The casting, okay? The solidification time is what? Proportional to what? The volume divided by the surface area, okay, of the casting. Okay? Because the rest of the terms inside the formulas are what? Constant. I already told you that, isn't it? Okay? So, when I produce a casting, my casting actually will what? Shrink. Correct or not? Will shrink. And last week, it was only last week, we talked about solidification. I told you how you can prevent the shrinkage. Shrinkage can be what? External or what? Internal. To prevent shrinkage, what do? I attach a what to the casting? Riser. Okay, I attach a riser. What does this riser do? What does it do? It will act as a reservoir, like a water tank. When shrinkage is taking place, you will supply what? Liquid metal to compensate for the shrinkage. But for it to act like the water tank, it means what? It must solidify last. If the riser solidifies first, no use, correct or not? In fact, if the riser solidifies first, you can get the reverse effect happening, That means the casting will be what? Compensating for the shrinkage in the riser. The reverse take place, That means your shrinkage in the casting will be what? Worse. Are you clear or not? So, how can I decide? How can I tell whether the riser is effective or not? How? You use what? The Chevron-Newell rule. Are you clear or not? Where you work out, make sure that the size and the shape of the riser is such that it takes a longer time to solidify as compared to the casting. Are you following me or not on this? Okay? Now, shrinkage, okay? Alright. When solidifications take place, okay, if I have a casting, okay, this is important. Alright, if I have a casting I ask you, how can you produce the casting that has no defect for me? How? First, I must add a riser. Okay? And then, that is not good enough. Adding the riser is not good enough. I must make sure the riser will what? Solidify slower than the casting. How do I ensure that? I already told you, use that rule. All this you must put in your description. Are you clear or not? Okay? And, okay, the other thing is this. I also told you last week. If I want my riser to be very effective, my riser should actually, that area should be attached to the casting. That part of the casting will become the what? Hot end. Are you clear now? If that part is hot, that means the liquid will keep on feeding to the casting. Okay? So, I need to have solidification taking place from the other end first. Okay? Then move towards the what? Riser. You see? If solidification is taking place from the other end, okay, there will always be liquid, isn't it? To keep on feeding. Right? Okay. So, what do? I need to have a cold end. I have a hot end which is attached to my riser. Okay? My cold end, how do I create my cold end? I put a piece of chill. That means nearby there, I can put a piece of metal or any good conductors, or maybe even a piece of graphite. Are you all clear with that? Okay? Alright. Now, I have a hot end, I have a cold end. That means I have a what? Temperature gradient. Can you mention this? Temperature gradient. Thermal gradient or temperature gradient. Temperature or thermal gradient will promote what? What's the word I used last week for you? Directional solidification. That means very good. It will take place, against the what? The thermal gradient from the what? Cold end towards the hot end. So you draw for me a diagram like what I draw for you. You put a riser, you put a chill, then you describe to me. Very good. You can do that. Okay? Alright. Now, we also speak about this. We spoke about in the ingot. Okay? I had got 3 zones in the ingot when I sectioned it. The outermost is what? The grain, how you describe it? Chill grain. Okay? Why is the outside chill? Why? Because of what? Chill means what? Very fine grain size on the outside. Why is it fine grain size on the outside? Why? Because very fast cooling rate. Very fast cooling rate. Very fast cooling rate means what? A lot of undercooling. A lot of undercooling means what? Small critical radius. Small critical radius means what? A lot of stable nucleus for solidification. That will end up with what? Fine grain size. Okay? Alright. So, the actually initial chill layers, actually that area there, my solidifications, what type of growth do I get? Grain growth? Dendritic. Are you clear or not? And you know when solidification is taking place, heat is given out. Remember we talked about the cooling curve, it goes down. After that it will come back to the what? You are undercooled, isn't it? Then you will come back to the freezing temperature, stay, and then after that. Now, why you will go up again is because why? Latent heat is given out. Are you clear or not? So eventually, as your solidification take place, all right, the temperature after it solidify, that zone there at the interface, the liquid will fall down to the what? The freezing temperature. No more undercooling. No more undercooling. So what happened? Planar growth will then take place from the surface. The surface will act as the what? The nucleating site for the what? Growth to take place. Alright, so this planar growth will take place. I end up getting what? What grain? What do you call that grain? Longish, columnar grains. Columnar grains. Okay, the columnar grains, okay, very long. Now, eventually in the center, I got a small bit of what? Liquid left. Small bit of liquid left. You know, if I got only a small bit of liquid but surrounded by solid, so not only then I will again lose heat, a lot of heat by what? Conduction. But because unlike the beginning, where cooling rate is very fast, here the conduction, may not be very fast, but it is still fast enough to give me what? Undercooling in the center. Are you clear or not? Okay, but because the cooling rate is slow, I get what? Very little undercooling. And we already said very little undercooling means what? I only get what? Very large critical radius. So I end up getting only very few what? Stable nuclei. Very few stable nuclei means what? I will end up getting what? Very large grain. Okay, so no more columnar grains. Okay, this one will give me what? What do you call that? EQX. EQX means what? Roundish. Okay, so that was for solidification, which we talked about. Okay, alright. Now, the other thing we also talk about under this what do you call it? Solidification is we will always encounter this gas problem. Gas problem? Okay. What are these gas problems? Porosity. How do we end up getting all this porosity? How? Why? You know, if you are asked a question like this, first you must draw the what? The solubility curve. Remember, we should show you a solubility curve. Okay, that I think in liquid state, very high solubility for gas. Then during solidification, a lot of it, there will be a sharp drop, correct or not, of solubility. And then solid state, very minimal solubility. Okay, so as I am cooling down my liquid, alright, the temperature drops, then go through solidification until solid. You'll find that most of the gases will have to be what? Ejected from the molten metal. Okay? And I already told you that during solidification, alright, as it is solidifying, you go through a stage where you are having a mixture of what? Solid and liquid, meaning that your liquid metal is semi-solid, and it is what? Very viscous. That's the word, viscous. So, if any gas were to come out from the molten metal, the dissolved gas were to come out, because, alright, the metal is so viscous, very difficult for it to escape. End up alright. Have you seen the Swiss cheese before? You know Swiss cheese, the Swiss emmental and many other type of all these cheese, very big holes, all this, and that's what you will get, in your casting when you section it. If I can share this with you, I was a foundry man, working in a foundry before. Alright, we produce those big castings, some can be up to 1 ton. Alright, for machine tool. It's an iron foundry. Okay, and this one we ship it out, Now no more foundries in Singapore, but last time, alright, we had. We ship it out to USA, Cincinnati. We ship it out to Japan. Alright? And we had these problems, Alright? When they do machining, down there, boom, they see all the holes. All the holes, So, usually if you are a manufacturer, you have got a warehouse, you procure components, you will have inventory, correct or not? Give you a buffer. So those people, every time we send there, alright, wow, maybe out of 10 pieces, alright, wow, many pieces reject, because of all these gas holes. So they have to go and use their inventory all start coming out, panicking, until all the way to USA, we fly the casting there. Okay, causes a lot of money. We went through that stage last time. Right? Then in the end, we found out that it was because during the manufacturing process, when you do cast iron needs carbon. Alright, needs carbon. So we were adding this carburizer, graphite, into the molten iron to boost up the carbon content. The carburizer contains a lot of what? Nitrogen. Okay? So that during when the casting solidifies the time, alright, it produces all these gas holes, nitrogen gas holes. Okay? So in the end, it took us quite a while and start panicking before we found out what was the actual cause of the problem. Okay? So this is gas hole, this is shrinkage. Can you imagine, like our case there, we send castings, overseas and all this, then we have this problem. Alright? So what would you do? When you produce the casting the time, alright, you need to make sure before you pour the molten metal, you need to remove the dissolved gases. This is known as what? Degassing. This is known as degassing. Okay? I told you there are two methods of degassing. One is what? Stream what through the molten metal? Inert gas, like argon. The other one is what? Use a vacuum. Okay, these two methods, last lesson we mentioned about this. Okay, so those were degassing. Okay? Alright. Let me. Yeah, okay, man. Are you okay? Are you okay? I run through the PowerPoint. Okay, so solidification. Alright, we talk about linear radius, minimum radius to give you a stable nucleus. Alright, then we talk about undercooling, cooling below the what? Freezing temperature. How much undercooling I have will depend on what? The cooling rate. After cooling rate, more undercooling. Okay, then can you see or not this relationship? Alright. Critical radius is what? Inversely proportional to what? The degree of undercooling. So if I cool very fast, I will get more undercooling. So my critical radius, according to this, will be what? Smaller. Okay, end up getting what? Q rate. Okay. Now this formula you must know, and must know. Okay, and do the example, in your what? In your book, okay, and make sure you convert your units to what? Your temperature to Kelvin. Freezing rate, don't add 273. The other you add 273. All right. Okay, so for heterogeneous nucleation, this one here, we must have what? Nucleating agents, alright, already said. And the more we add nucleating agent, the smaller will be the grain size. So we can call them grain refiner. Add more means what? You do more refinement. Alright. And so this one here, can you see grain size strengthening? I mentioned to you grain size, fine grain size fluctuates because of the grain boundary. Okay? And I can either add what? Solid particles into my molten metal, or I can have alloying elements. These alloying elements will dissolve into the molten metal, and then they will have reactions to form what? These are solid particles. Okay, like in this case here. Okay, this one. Okay, we have got planar growth, and the other one is what? Dendritic growth. Planar growth refers to what? More heterogeneous nucleation. Dendritic is what? Homogeneous nucleation. Okay, so dendritic growth. And then this one here, you know the solidification time is proportional to the ratio of what? Volume over area, surface area. Okay, and this one here. Okay, macrostructure. Can you sketch this? Sketch this. Okay. Then we have got the three zones: chill zone, columnar zone, and the what? Flux EQX zone. Sketch them and know how you get all these three zones. Okay. All right. Then the two defects, we have got what? Shrinkage defect, and the other one is what? Gas porosity. Okay. So you need a riser. For shrinkage, you use riser. For gas porosity, you do what? Degassing. Degassing is what? You do use inert gas. Alright, degassing, or you do what? Vacuum degassing. Okay. Then we talk about what? Directional solidification. This is not inside here, but I already told you how you can do it. Directional solidification, I must set up what? A temperature gradient, meaning I must have a hot end and a cold end. The hot end, I attach a riser, cold end, I add a chill. Okay, to give me the temperature gradient. Okay? Alright. Okay, done. Okay, so large EQX grain is due mainly to what? Large EQX grain. Why do I get large EQX? Why? In the center. It's because of what? Very slow cooling. Okay. And then, okay, okay, how you can prevent shrinkage? I need to have, you know, if I give you the casting, you can describe to me. Just now I told you what I think I am looking for. Okay, you must also mention the rule, you know, solidification rule. Okay, okay, you should have no problem. Alright, everything I already mentioned. Okay, alright, can we do the phase diagram? Now, then after that we take that's it. Okay. No, anyone got problem? Anyone got problem? Okay, we finish in half an hour. This one, okay. Phase diagram. Okay. All right. Okay. Now, we securely real diagram. Okay. All right. Now, we were talking the last week. All right, about solid solubility. Can you remember that? No, solid solubility. And when I got two elements in an alloy, I will call that a what? Binary alloy. Remember, no? Binary, two. When it is completely soluble, now you don't worry about partial solubility. Now we are only talking about what? Complete solubility. Right? Very easy. When it is completely soluble, your alloy is a what alloy? Isoformous. Binary alloy. Remember or not? We talked about that. Isoformous. Okay? And for isoformous binary alloy, how does your phase diagram look like? How? Here is what? What is it? Temperature. Okay? And let's denote it by A and B. So here is, let's say, percentage A, this direction. Okay? So here, since A goes this direction, here must be what? 0% A, and here must be what? 100% A, and that means here I have got pure A, and here what do I have? I will have what? Pure B, because it is 0% what? A. Alright? When it is in the center, it will be what? 50% A. If it's 50% A, the other remaining one must be B. So the two add up must be 100%. Are you clear or not? Alright? And how is the shape? Okay, if I have isomorphous,